Hello and welcome to Engineers Mindset Academy. So in today's video, I'm going to show you how to derive the basic equation of a thin shell cylinder with hemispherical ends, as can be seen on the board. Now, before going into that derivation, let's first of all understand what a cylinder is. A cylinder is simply a component which is used to store fluids at high pressures. Now, the cylinder can either be a thin shell cylinder or it can be a thick shell cylinder. It all depends on the thickness of the cylinder involved. There are three basic types of stress that takes place in the fluid inside a cylinder. The first stress is called the hoop stress. The first stress is called the hoop, or you can call it circumferential stress. The hoop or circumferential stress, okay, symbolized by sigma H, where H stands for hoop and of course sigma stands for stress. The second type of stress is simply called the longitudinal stress. The longitudinal stress, okay. The second type of stress is simply called the longitudinal stress, symbolized by sigma L, where L stands for longitudinal and sigma stands for stress. And the third and final type of stress in the fluid inside a cylinder is simply called the radial stress, okay. We have the radial stress, simply sigma R. Now, the hoop or the circumferential stress is simply that stress which acts at 90 degrees to the circumference of the cylinder. It is that stress which acts at 90 degrees to the circumference of the cylinder, whereas the longitudinal stress is simply that stress which acts parallel to the circumference of the cylinder. The longitudinal stress is simply that stress which acts parallel to the circumference of the cylinder. The radial stress is actually a very minimal stress. It acts along the radial axis of the cylinder. So in most cases, it is usually neglected because it has a very minimal value and hence it can be neglected. Now, the hoop stress and the longitudinal stress make an angle of 90 degrees to one another. So you have something like this. You have the hoop stress which acts at 90 degrees to the circumference of the cylinder, and then you have the longitudinal stress which acts parallel to the circumference of the cylinder. Now the hoop stress and the longitudinal stress are at 90 degrees to one another, and this simply makes them a principal stress. So these two stresses, the hoop stress and the longitudinal stress, are principal stresses. Since they are principal stresses, then we have the maximum shear stress between the two principal stresses, okay. The maximum shear stress, okay, the maximum shear stress, tau max, is always taken as the hoop stress minus the longitudinal stress divides by 2. So this is the equation to find the maximum shear stress between the hoop stress and the longitudinal stress in a fluid inside a cylinder. Now, how do you find the hoop stress? Mathematically, the hoop stress can be obtained using the equation, okay. The hoop stress can be found using the equation P times D all over 2 times thickness, where P stands for the pressure. P is equal to the pressure of the fluid inside the cylinder, pressure of fluid, okay, the pressure of the fluid inside the cylinder. D itself stands for the diameter of the cylinder, okay, diameter of cylinder involved, and T stands for the thickness of the cylinder, okay. T stands for the thickness of cylinder involved. So to find the hoop stress, it is simply the pressure of the fluid multiplied by the diameter of the cylinder divided by 2 times the thickness. Whereas to find the longitudinal stress, sigma L, to find longitudinal stress, we simply employ the equation pressure times diameter all over 4 times the thickness. To find the longitudinal stress, you simply employ the equation pressure times diameter divided by 4 times thickness. Now the parameters here still remains the same: P for pressure, D for the diameter of the cylinder, and T for the thickness of the cylinder. Now, comparing these two equations, you're going to find out something. Comparing these two equations, you're going to find out that the hoof stress is actually what? 2 times the longitudinal stress. Comparing these two equations, you're going to find out that the hoof stress, sigma h, is actually what? 2 times, okay, is simply 2 times the longitudinal stress, okay? The hoof stress is simply 2 times the longitudinal stress. Now, how is that so? Let's prove this and see. Hoof stress is equal to, we said 2 times longitudinal stress, and this is the formula for longitudinal stress. So which means if I multiply this formula by 2, I should be able to obtain the formula for the hoof stress. So this is simply saying 2 times the longitudinal stress, which is pressure times diameter all over 4 times thickness. Okay, so you have 40. So observe here now that 2 goes into 2 is 1, 2 goes into 4 is 2. So this simply implies that hoof stress, okay, hoof stress is equal to, from here I am left with what? T times diameter all over, now I have just 2 left as the denominator here, it becomes 2 times T. So which means the hoof stress is always 2 times the longitudinal stress. Alright, so keeping this in mind, let's fall back to this side. We said that since the hoof stress and the longitudinal stress makes an angle of 90 degrees to one another, they are therefore principal stresses, and hence we will need to find the maximum shear stress between the two. The maximum shear stress is always given as the hoof stress minus the longitudinal stress divided by 2. So this simply means that tau max, okay, is equal to, we know the formula for the hoof stress. Hoof stress is simply what? Okay, or we can simply employ from the shortcut. We said that hoof stress is twice longitudinal stress. So in place of hoof stress here, this becomes 2 times the longitudinal stress. So 2 times sigma L minus sigma L, okay, minus sigma L divided by 2. So this is going to now be what? 2 sigma L minus sigma L remains sigma L divided by 2. So which means this simply implies that the maximum shear stress, tau max, is simply what? 1 all over 2 times the longitudinal stress. As can be seen here, the maximum shear stress is simply 1 all over 2 times the longitudinal stress. Okay, so if I put in the real formula for the longitudinal stress, then it means maximum shear stress becomes 1 all over 2 times the longitudinal stress itself is P times D all over 4C. So this simply means PD times 1 remains PD all over 2 times 4 gives us what? 8C. So this is another formula for the maximum shear stress. So tau max is simply PD all over 8C, as can be seen. So either this or this can go for the formula. So in essence, or in general, what I've said so far is that hoof stress is always twice the longitudinal stress, and the maximum shear stress is always half the longitudinal stress itself. And I said earlier that the hoof stress and the longitudinal stress makes an angle of 90 degrees to one another. That simply makes them what? Principal stresses. And as such, there's a need to always find what? The maximum shear stress between the two principal stress. So we are going to be keeping these equations one side, then we can now move on to what? Deriving this particular equation. So I'm going to pause the video here and rearrange these equations one side, then let's start to derive the formula for the thin shell cylinder with hemispherical ends. All right, welcome back. So remember earlier we said that the hoof stress is given as PD all over 2T, longitudinal stress is given as PD all over 4T, and the maximum shear stress is given as PD all over 8T. And in general, we simply said that the hoof stress is usually 2 times the longitudinal stress, and the maximum shear stress is usually half the longitudinal stress. Now let's consider this cylinder. This is a thin shell cylinder with hemispherical ends. Now, these are the hemispherical ends, the portion involving the bends. Okay, this is a hemispherical end because we have a hemisphere there. Okay, so simply a hemisphere end, simply a hemispherical end. Okay, same thing as here. This is also a hemispherical end. So we can simply use hemisphere as the short form, hemispherical end, whereas this is called the cylindrical portion. This is called the cylindrical portion. This is called the cylindrical portion. Now, let the thickness of this part, which is the hemisphere now, the thickness of the hemispherical portion be T2. Call this T2. Also call here T2. The thickness of the hemispherical portion. That is where the bend is found. Whereas, let the thickness of the cylindrical portion be called T1. So, call here T1. That is thickness of the cylindrical portion. This is the cylindrical portion, whereas the bend is the hemispherical portion, and D here remains the diameter of the cylinder itself. D remains the diameter of the thin shell cylinder itself. Now, in order to be able to solve for the basic equation of the thin shell cylinder with hemispherical end, the first thing to do is let's start analysis of the cylindrical portion first. So, considering cylindrical portion, okay, considering cylindrical portion, considering cylindrical portion. All right, so you find the hoop stress in the cylindrical portion, you find the hoop stress and the longitudinal stress in the cylindrical portion. So hoop stress, which is sigma h, remains PD all over 2T in the cylindrical portion, whereas the longitudinal stress, okay, longitudinal stress, which is sigma L, remains PD all over 4T in the cylindrical portion. Now, having found the hoop stress and the longitudinal stress in the cylindrical portion, the next thing to find is the strain in the cylindrical portion. Okay, the strain in the cylindrical portion is given as the hoop stress divided by Young's modulus. Remember from the idea, Young's modulus is always stress all over strain, and therefore if you make strain subject to the formula, this becomes what? Stress all over Young's modulus. So this is the idea. Okay, Young's modulus is always stress over strain, hence if you make strain the subject of the formula, it becomes stress all over Young's modulus. So the strain in the cylindrical portion is simply given as a hoop stress all over the Young's modulus, but minus the longitudinal stress all over Poisson ratio multiplied by the Young's modulus, where M stands for the Poisson ratio. Okay, M there stands for the Poisson ratio. So be very careful of this. Okay, M stands for the Poisson ratio. The strain in the cylindrical portion is simply given as the hoop stress all over Young's modulus minus the longitudinal stress all over Poisson ratio multiplied by the Young's modulus. You simply have this. Now let's put in their parameters, but not forgetting, recall we said that hoop stress is 2 times the longitudinal stress. So recall, hoop stress is actually 2 times longitudinal stress. Having this in mind, let's plug it back into the equation. That means the strain at the cylindrical portion is simply given as, in place of hoop stress, we have 2 times the longitudinal stress all over the Young's modulus, okay, minus the longitudinal stress itself all over the Poisson ratio multiplied by the Young's modulus. We simply have this. All right, so let's continue from here now. We have now that the strain itself is equal to 2 times the longitudinal stress all over the Young's modulus minus the longitudinal stress all over the Poisson ratio multiplied by Young's modulus. So if you observe from here now, the longitudinal stress is quite what? Is factorizable from here. Since they are the same, you can factor out one of them. This simply becomes longitudinal stress multiply now by, I am now left here with 2 all over Young's modulus. This becomes 2 all over E minus 1 all over M E. So I have something like this, okay? But then we are considering the cylindrical portion. Since you are considering cylindrical portion, the thickness of the cylindrical portion, we call that T1. So that means we need to find the longitudinal stress at the cylindrical portion. Longitudinal stress is equal to, we said that longitudinal stress is equal to pressure times diameter all over 2 times thickness. Now, what is all over 4 times thickness? Now, what is this thickness? This thickness is simply the thickness of the cylindrical portion, since we are considering cylindrical portion first. So this simply becomes P times D all over 4 times what? T1, where T1 becomes the thickness of the cylindrical portion, since we are on the cylindrical portion here. Okay, so we fall back now into this equation. This simply means that the strain due to the cylindrical portion is simply equal to, in place of the longitudinal stress, we have pressure times diameter all over 4T1. Okay, and this is now multiplying 2 all over Young's modulus minus 1 all over Poisson ratio multiplied by the Young's modulus. So let's simply call this equation 1. All right, so let's simply call this equation 1. So this becomes the strain analysis, or the value of the strain at the cylindrical portion. Now, having done with the cylindrical portion, we repeat the same procedure for what? The hemispherical portion. Find the value of the strain at the hemispherical portion. So this is what I'm going to do. I'm going to be wiping all of this now, and of course start afresh for the hemispherical portion. Okay. All right, guys. So this is the equation we obtained earlier for the strain, where we consider the cylindrical portion. But let's still touch this equation a little bit. So if you take a look at this equation, you observe that Young's modulus is constant or common between these two, so it can also be factored out. So we can simply factor out Young's modulus. This becomes 4T1 times E. Okay, so to simply take off this Young's modulus over here, this becomes just 2 minus same thing here, factor out E. So Young's modulus is common, you can factor it out. Okay, so we can simply call this our equation 1. All right, so for the strain in the cylindrical portion, now we are considering the hemispherical portion, which is the bend. Now, one thing to keep in mind when considering the hemispherical portion is that the hoof stress is equal to the longitudinal stress at the hemispherical portion. Okay, at the hemisphere, the hoof stress, sigma h, is equal to the longitudinal stress, and this is given as PD all over 4T. We have done all of this earlier, okay? PD all over 4T. If that's the case, then that simply means that the strain, now we have to move on straight down to the strain. The strain, remember, the strain at the hemispherical portion is simply, call this strain 2. Let's also call this strain 1. Okay, so strain 2 is now equal to, this is now going to be, remember, the hoof stress all over the Young's modulus minus the longitudinal stress all over what? The Poisson ratio multiplied by the Young's modulus. This is the equation for strain. Now, this is going to now be equal to, we said, at the hemispherical portion, the hoof stress is equal to the longitudinal stress. That means in place of hoof stress, we simply write this to be what? Longitudinal stress. So this becomes longitudinal stress all over Young's modulus minus longitudinal stress all over Poisson ratio multiplied by the Young's modulus. So you have something like this. So strain 2 is now equal to longitudinal stress and Young's modulus are common. You can factor them out. This becomes longitudinal stress over Young's modulus. Now multiplying, I am simply left with 1 minus 1 all over the Poisson ratio, such that this longitudinal stress over Young's modulus multiplied by 1 simply gives us back this equation, and of course this multiplied by 1 all over m gives us back this expression. So this becomes the expression for the what? Strain in the hemispherical portion. Now, what is longitudinal stress? Remember, we are talking about now the hemispherical portion, the bend, and the thickness about the bend is what? T2 and not T1. So that simply means that the longitudinal stress about the hemispherical portion becomes pressure times diameter all over 4 now it's going to be what? T2, okay, because we are at the hemispherical portion and the thickness of the hemispherical portion is T2. Hence, the thickness about that becomes T2. So the longitudinal thread becomes PD all over 4T2. Now, if you know this, you can simply plug this into this equation. All right, so we are going to now have, let's strike here off. So I can take this off now. Okay, so we are going to have strain 2 to be equal to, this becomes P times D all over 4T2, not forgetting there is a Young's modulus there, so multiply by Young's modulus into, I have 1 minus 1 all over M. All right, so I simply have this. So you can simply call this equation 2. So this is the strain at the hemispherical portion and this is the strain at the cylindrical portion. Now, at the point of equilibrium, the two strains are equal. At the point of equilibrium, that is simply saying to prevent uneven distortion or straining at the junction between the hemispherical portion and the cylindrical portion. To prevent uneven distortion at the junction between the hemispherical end and the cylindrical end, then the two strains must be what? Equal, to prevent uneven distortion or uneven distribution at this junction. The two strains must be equal. So at equilibrium, okay, at equilibrium, equation 1 is equal to equation 2. At equilibrium, the both equations are equal, so you simply equate these two. Now you have, for equation 1, PD all over 4T1 times Young's modulus into 2 minus 1 all over M, and this is equal to equation 2, which is PD all over 4T2 times Young's modulus into 1 minus 1 all over M. You simply have this. Since they are equal, then the pressure in the cylinder, of course, the pressure of the fluid in the cylinder are the same. Diameter of the cylinder is still the same as can be seen here. Diameter remains the same. So which means pressure cancels pressure, diameter cancels diameter, same thing, 4 here cancels 4 here. The Young's modulus also cancels the Young's modulus. So what I am left now is simply 1 all over T1 multiplying 2 minus 1 over M, and this is equal to, same thing here, 1 all over T2 multiplying 1 minus 1 all over M. I simply have this relationship. Now, this is what I want to do. At this juncture, simply take the LCM of the terms in the brackets. Take the LCM of the terms in the bracket at this point. You simply take the LCM of the terms in the bracket. Let's continue that over here. So we have 1 over T1. Now, in this bracket, LCM here is simply M. So we have M all over. Now, this is 2. Of course, M divided by, this is same as 2 all over 1. Okay, 2 remains 2 all over 1. So M divided by 1 remains M. M times 2 gives us 2M minus, again, M divided by M is 1. 1 times 1 remains 1. So I have this. And this is equal to the same result on the other side, 1 all over T2 into LCM also remains M. Okay, LCM remains M, and this one is same thing as 1 divided by 1. So M divided by 1 is M. M times 1 gives us M minus, again, M divided by M now is 1. 1 times 1 remains 1. So we have this. Okay. So at this point, let's expand the bracket using the terms outside. 1 multiplies everything at numerator here remains 2M minus 1 all over T1 multiplies M here gives us T1M. And this is equal to, same thing, 1 multiplies everything here remains M minus 1 all over T2 multiplies M here remains T2 times M. Okay, now this is what I will do at this point. Simply cross multiply at this point. You simply cross multiply, let everything at this top multiply down here, and let everything down here multiply top. So we are simply changing positions now. Let T2M move up here, and let 2M minus 1 move over to this side. If that happens, this simply implies T2m moves up here, becomes T2m all over, I have a T1m, and this is equal to 2m minus 1 takes the position here. So I have up here m minus 1 all over 2m minus 1. I have something like this. So from here, m cancels m. I have now, this simply implies that T2 all over T1 is now equal to m minus 1 all over 2m minus 1. And this is the basic equation for a thin shell cylinder with hemispherical ends. The thickness of the hemispherical portion divided by the thickness of the cylindrical portion is equal to the Poisson ratio minus 1 all over 2 times Poisson ratio minus 1. And you have this. So it all boils down to this side. Once you get to this point, all you need to do is what? Do a one-sided cross multiplication. Just a one-sided cross multiplication and changing of position. So 2m minus 1 simply takes over the position of T2 times m, and whereas T2 times m takes over its own position, and you have that equation. This is the basic equation for a thin shell cylinder with hemispherical ends. All right, guys. So in general, we've talked about the hoof stress, we've talked about the longitudinal stress, we also talked about the radial stress, and I also explained the connection between the hoof stress and the longitudinal stress at 90 degrees, which makes them principal stresses. And I gave their formulas. I also talked about the maximum shear stress which exists between the two principal stresses and their formula as well. So in the next video, we are going to be employing all these equations to start solving problems under thin shell cylinders. I will see you in that video. Thanks and cheers.